When you click on that arrow, that will open up another page. Look like this, and then there's 4 options generally. Click on the last option called lab, okay? And also download the lab datasheet. Lab datasheet, that should be look like this Excel page right here, okay? There should be 3 tables, and then there are 3 graphs. And also there should be space for the figure, okay? Simulation figure. And this lab and then onwards another maybe like 2 labs. We're going to do short lab reports. After lab number 8, there's no lab report at all. You will be doing only lab data sheet, okay? But however, altogether you must complete 8 lab reports and then all the data sheets. So pay attention to those things. If you miss 1 or 2 labs in the beginning, then you can still submit the lab report later in the semester, okay? All right, so let's take a look what we try to do, and then by now you should have a really good idea about the projectile motion. So the projectile motion means object is sending to the space with an inclined angle from the horizontal x-axis, right? That's what the projectile means. When you send an object to a space just to the upward direction with some inclined angle from the ground, then object is under gravity after it move away from the ground. Because of that, y-axis and x-axis behave very differently. So the projectile motion can be easily understood by looking at x-axis motion and y-axis motion separately. After objects send away from the ground, x-axis motion is independent of the gravity. Because of that, there's no any acceleration effect. Because of that, only on x direction, you have only one equation to work with. That is actually equation number 2. That's the only equation in a projectile motion apply for the x direction or the horizontal direction, okay? So what it says you there, the total displacement is equal initial x velocity times the t. So this x is actually generally called as the range. Range means how far object travel on horizontal axis relative to the starting point, right? So that's the only equation for x direction. However, y direction, you can apply all 3 linear equation you've been learning in your lecture class, okay? Usually, when an object moving on a straight line, there's a standard 3 equation we are using. All 3 are valid for the y-axis direction, okay? So which means I can apply y equal y0 half gt t squared. If object doesn't have the initial velocity, equation number 4, equation number 3 is the generally standard equation. Y equal y0 is the initial y component and initial y displacement times the initial y velocity times the half acceleration times the t square. This ay is the gravity now. But if I send the object above the ground, like in this picture above the ground, but horizontally initially, which means initial velocity is only horizontal. As a result of that, initial y velocity right here becomes 0. Then this whole part becomes 0. Equation number 3 is actually reduced into this format. Okay. And which means I can apply easily this equation to figure out what's the correlation between the time and displacement. For example, if I know how height object is actually sending, then I can find how much time object is on there. So that generally called the time of flight, right? How much time is object on there, for example. So that actually one important equation for today's experiment, right? So then there's 2 other general equations you can apply for the projectile motion. Those are still valid, but we don't need the other equation. We need this equation, and also we need actually x displacement equation for some calculation. Okay, that's the plan. Any question? Everybody have the simulation? There's 4 different options you can see on this page, very bottom. There's 4 different options, so you need the last option called the lab, okay? And right hand side, you see a couple of other options we can test with the air resistance, which we're not going to do today. And then we can change the gravity, for example. I'm talking about right hand side, this brownish color, this box. I can change the gravity, but that also we're not doing anything today because we need to study the air. We need to study the gravitational acceleration on our Earth, right? So that should be, leave it as a 9.81. And then we can change the object mass and diameter that we actually gonna test. What is the effect of mass technically? Gravitational acceleration should not depending on the mass. Because of that, the projectile motion should not depending on the mass. So we're going to test that. And then right here, you can see different option, which mean we can send different object. So that we're going to test out quickly what the effect of the different object. And then couple of other options here. If you bring this one, this can measure. This is a sensor. When I place somewhere, it can measure how much the projectile stay on the air, time of flight, for example, the range, x-axis displacement, height, y-axis displacement, and so on. There is another icon here which we don't need. That's a regular tape of measurement. We can actually measure the displacement by using that too. And also we can measure the displacement by using this red circle right here. But we, instead of using that, actually we're going to use this sensor. Okay, that is easier. And then on very bottom, you can see right here, this object, which actually fire the projectile. And in this place right here, you can see a positive sign. So you can click that and then drag upward and downward. You can see the height of the object position can actually change depending on that. What height we need, I can actually click and drag accordingly, okay? And if I want to send the projectile in an angle, I can do that. Or if I want to just project the object horizontally, for example, that's what actually planned for today's experiment. Then I have to change this angle all the way to 0 because all standard angle we measure from positive x, right? So I need to bring this all the way to 0. Then object is actually sending initially, object velocity is only this direction. So that way we can easily use this equation earlier we discussed, because if I'm using equation number 4, initial y direction velocity v0y must be 0, right? So that's why we're going to send the object horizontally first, okay? And then below here, you can see a speed selector, which means I can actually click and drag this and then change the initial objective speed accordingly. Okay, and also we can observe this in slow-mo mode. That I don't think we need it, but in case we need it, we can actually observe the motion in slow-mo mode, okay? So that's all the functionalities, and then let's take a look what the lab manual asking. We're going to slowly proceed all the table. As we proceed the table, this lab has a different section. You can see I put the section number here. There's a part 1 and then part 2 and then part 3. You can see part 4 is not here, instead part 5, 6 and 7 there. Part 4 is actually, I don't think there's anything meaningful there. You can read that part. It's just asking you to find it out, the displacement by using this one. That we're going to do in a different way, okay? So that part we don't need to worry about too much. And then at the end, there's a couple of extra credit questions which are not mandatory, okay? Which are not mandatory, and this is extra work. If you want, you can do it. That also not mandatory. Because of that, this lab manual also does not contain post-lab question, okay? Last manual also, there wasn't a post-lab question. So if there's no post-lab question, when you do the lab report, you can skip that part, okay? After reference, then you can skip. But one thing actually, you can see references are given like this. Do not copy paste this into lab report. This is not the right way to do the references. There's a standard way you have to put your references in the report. Generally, references are 2 textbooks you can refer. One textbook which I gave it in my syllabus. The second textbook, your in-class textbook. Third one is actually this lab manual, okay? None of these are considered as references in standard scientific writing style, okay? Do not put any YouTube links or anything that actually not considered as references at all. So if you want to learn how the references are look like, because I'm telling this, some student still seems to be not really familiar to do the references and things like that. So please take a look this sample report, and also you can take a look my week 1 lab manual, okay? If you open the week 1 lab manual that has a standard IEEE format, how it closely match with the APA or MLA style, you would say, in terms of writing classes. That's the way we put the references, okay? If you put in the link, then before the link, we have to have all the information about that particular reading material, okay? Then only we're going to put the link. Otherwise, we just not putting a link without any information. That's not really correct, okay? Please make sure you corrected out all of those when you do the lab report. We're going to do only few uh, short labs. In terms of detailed lab, you're going to do, I think, only one. That is the last lab. And then two or three more short labs. Then if you complete 8 labs, then you don't need to worry about lab report at all. At the end of the second half of the semester, you're just completing only data table, okay? But all the data tables are mandatory. Okay, any question? So please make sure you corrected, especially when you do the references, don't copy paste any of these, okay? So those are actually given here not to use as references. These are given here as a learning material, okay? If you like to learn more about the projectile motion, things like that, you can actually use them, okay? That's the idea. And right here, you can see another learning material. All of these are actually for your extra learning purposes, okay? Do not misunderstand that. There's a couple of links given here, and then I should copy paste this into my references list. No, that is not correct. Okay, any question? All right, then let's take a look part by part. As we complete the table, all these sections going to be completed automatically, okay? First part is that we're going to study the range versus mass of the projectile. So let's go to table number 1. And then what we're going to do, we're going to keep the initial velocity about 12.0 and the initial height about 15. You can see those two numbers. I leave it there because we're not going to change that. Instead, let's change the type of the object. So basically, instead of selecting, I can select the one object and then select the mass, or I can actually change the type of object. That may be much easier. Let's do that. So let's do initially cannonball. So you have to type here the object type, okay? Object type, cannonball. And if you don't have enough space there, you can actually click and drag this very top end. Then you can make a little bit of space on this cell. Okay, cannonball mass. I can select a different mass, but leave it what it's showing automatically instead of selecting that. So it is automatically giving you 17.6. Let's leave it like that. And then mass we measuring in kilogram. And then initial velocity we're going to measure meter per second. Make sure you add those units accordingly. Okay, sorry, meter per second. Meter per second. Initial height, we're going to use the maximum height possible. You can see I can click and drag this, right? The maximum height you can go 15 meter, you can see here. So leave it like that. So which means this is in meters. And the range, that's what we're going to check, okay? By changing the object type, we're going to see whether the range is different for different object or the same, okay? A range we're going to measure by using meters. After cannonball, after cannon fired, we can actually bring this sensor to measure the range easily, okay? Otherwise, we can actually bring this one too, but this is easier. All you have to do fire this by using this button right here on the bottom. And I have object there now selected, right? Cannonball with the 17 kilogram heavy object. And the initial velocity, we're going to give 12 meters per second. Let's fire that. That's our projectile. Now it shows the path, leave it like that, okay? And then let's bring this sensor and then measure what's the maximum range it travel. So the time of flight is about 1.75 seconds. The range is about 2273. So let's write that one here, 2273. I think I formatted all of these cells into 2 decimal places. If you don't see it, you know how to reformat, right? Click on any cell, right click, format cell, and then number decimal places to 2, okay? But I remember I formatted the Excel sheet accordingly. Question?
No, Professor.
Oh, initial, sorry, actually initial speed I had to change here. Yeah, let's retry that. Because I put here 12, but right now it has 13, right? To change that, you can click and drag this selection tool, or you can use these arrows. Okay, let's do 12. It's not big deal, really. We just check in this, but we have to follow these numbers, right? Otherwise, you change this number. So let's retry this very quickly. Yep, we need to change that. And then fire it again. Now you can see if I change the speed, now it is not the previous spot right here. Okay, let's measure that. And when you bring this, you can see when that cross sign middle goes to the exact point, it will becomes highlighted. It's easy to point it out, right? Bring it and then bring it closer and closer. When it highlight around that point in white color, then you can stop there, read that number, 20.98. 20.98. You can see one thing there, that time is actually, you can see it's the same as the previous number. See that? So which tells us some idea about the time of flight is not depending on anything. It depending on actually height and the initial velocity. It's height actually only. Because initial velocity vertical direction is 0. Because of that, the time of flight vertically is only depending on that height. As a result of that, total time of flight horizontally is also depending on only that initial height, not the initial horizontal velocity component at all. Okay. Okay, question. Then let's check this out. So to check this out, you have to change the different object, right? Then let's take a different object. I can change the mass here instead of just select the whole object. Tank shell, let's send that. Tank shell. Okay. Object mass, let's use this number given here. Okay, 42 kilogram, very heavy. And let's keep the initial height and the initial velocity as it is. And then let's fire. You can see that goes exactly on this previous line, okay? You see that? If you click this eraser sign right here, all the previous line disappear. It's better to let all the previous line disappear and then refire this. Okay, now this is new projectile, and then let's bring and take a look. See that time of flight is same. The range is also same. There's no difference at all, 20.98. So which means the range is actually, the whole projectile is not depending on the object. You can see these are very different objects to each other. One has a mass 17, which is a cannonball. The other one has almost twice that mass, and it is a completely different object. But everything depending on how high the object is and the initial velocity components, okay? Let's erase that and then continue to check the other objects. So let's take a look at the golf ball. Golf ball, keep everything same. The mass of the golf ball, let's keep it like that, whatever it's gave originally, right? 0.05, the number right here I'm reading, okay? And then let's do the same. Keep the initial velocity, initial height, fire it, and then let's measure the horizontal range. So you can see time of flight and the horizontal range never affected, right? So which means those are only depending on initial height condition, okay? Erase that, and then let's do the next one, baseball. Baseball mass is about 0.15 kilogram. Fire it, and then check the range, exactly same. It seems to be the object initial mass, object mass, or the size or the shape not really matters at all. Okay, that's one indication of this gravity is independent of mass, right? Gravity is acting same way for every object, everything around the Earth's surface. This is another good indication of that. So you shoot an object, height 50 meters above with the same velocity horizontally, projectile path is exactly the same. So that's a good, very good indication that the gravity is independent of anything. Okay, so let's continue, check the other stuff very quickly. Football, there's nothing new to check here, but let's complete anyway, all the objects given there. Football, erase it, fire it, and it should go exactly to the same place. There's no difference at all. Let's record the mass of the football. Different masses will appear accordingly because of that. And let's erase this and select the next object, pumpkin. Mass is about 5 kilogram. Pumpkin about 5 kilogram. Let's check how far it's gonna go. Exactly the same, no difference at all. I can click and drag actually this one as we go down. Instead of typing, it's the same number. Erase the path, select the next object, human. Mass is about 70 kilogram, a little bit heavy, but that's okay. All right, so that's a human guy. So the same thing. I'm gonna click and drag this one instead of typing, right? If you click on the cell and then right-hand side, very bottom, you will see that solid green dot. And then if you click and drag, it will fill up the next cell with the same number. Okay, let's check a couple of other stuff here. What else here? Piano. Okay, let's send the piano. And then see how far it goes, piano. So it's very heavy, 400 kilogram. And should not show any difference at all, right? See that? Exactly the same. And the last object, I think a car, let's send that. Car is about 2000 kilogram, very heavy. Erase this and then send the car, exactly the same. So that's the idea of actually gravity. You can get a really good idea by looking at those numbers. So none of these numbers are affected by the size or shape of the object, okay? Question. Let's take a screenshot also for this one. Since we're doing only short lab reports, this point and onward, only few of them, all of these information in the data tables must goes to the data section on your short lab report, okay? Because there's no procedure section to apply this, add this picture. Because of that, even this picture, put it into data section, okay? Otherwise, that must go into a procedure section. Let's add that picture here. What we have, screenshot this guy. You can crop out whatever unnecessary, right hand side very top, and then this dark black arrows you can bring and then separate out. And maybe that area is good enough. Okay, click the crop again, and then you can have a nice picture there. Okay, and that's our simulator. All right, so let's continue. So then in the discussion, you have to discuss, right? So every table, even though we writing the short lab report, data section, discussion and conclusion, references, those three must be really completed, okay? Which mean in the discussion section, you have to discuss about all of these tables. Each table, write up a couple of sentences. Then you can easily fill up half a page or full page of a discussion. Question? Okay, then let's continue to the second one. In the second part, we're going to investigate the effect of initial velocity, right? We can change the initial velocity from lower number to the higher number. And then we're going to pick one type of object, one type of mass, one mass, and then we're going to check the initial velocity effect, okay? No. Discussion going to come only for the lab report. This data sheet is just submit whatever you have by tonight, okay? Yeah. Data sheet is very similar to like we're doing so far. Just complete everything, then tonight upload this Excel sheet. Okay, now what we select? We can select a different object, but let's select like a cannonball, or maybe you can go just custom. That also fine. And then it is 100 kilogram. That seems to be too big. Let's pick a different object. Maybe a golf ball. Doesn't matter. That's your choice. Okay. You can pick any, write it down accordingly what you pick. Okay. You don't need to necessarily follow the lab manual, the information, or necessarily follow the what I says, but you have to complete what we're trying to do here. Okay. You have freedom to select if you want a different object here. I'm not going to reduce any point or anything because you know now, doesn't matter what I select. What matters is that initial condition, right? So let's pick a golf ball and then let's change the velocity of that, right? So I'm going to pick golf ball and the mass of the object. I'm going to keep it like that, the original mass given. We don't need to worry about that. We know there's no effect on that either, right? We just test that, but we need that information here for our informational purposes. And then let's select the initial velocity and then check the initial height, and then select, then we'll check how far it is moving as a function of when I change the velocity. And then also we're going to check the time of flight. Okay, that's the plan for the case number 2. Okay, range versus launching speed, height and mass remaining constant. Okay. Okay, then let's see. We can go maybe lower speed to higher or higher speed to lower. That also doesn't matter, but let's go some lower speed and then slowly increase the speed, right? Let's go maybe like 5 meter per second to some high number. So which means this is going to be meter per second. And the initial height, we're going to keep that fixed in unit meters. We're going to keep it on 15 fixed. Okay, we're not going to change that. Initial velocity, now I am on 5. Range of the projectile and the time of flight we're going to measure from the simulator. Range going to be unit meters. Time of the flight or the time of the projectile going to be second. Those two we're going to measure from the projectile. Okay, you can erase and then fire the object. Make sure angle should be 0. Okay, because we're firing horizontally. That's main plan of the this lab. Okay. You can see now it drop into here very close by. We can bring the sensor and then measure this. And it is now 8.74. That is the range horizontally, and then time of flight 1.75. Let's increase this by maybe 3. Let's try 8. And then 15 going to be remaining fixed. Let's erase the path and then click the fire button again. Now you can see it went a little bit further, right? So it means as a function of horizontally speed changes, it actually go a little bit further horizontally. However, if you keep looking at the time of flight, that's depending on only this initial height. The reason when object moving horizontally initially, there's no vertical component at all, okay? Because of that, the time of flight is still the same. However, it can go further because we're giving more power initially horizontal direction. Okay, that's why. Now you can see it changes to 13.99 and then this is still remains the same. Let's try maybe 12. Erase the path, fire again. Okay, it went further now. It's about now 12 initial velocity, initial height same 15, the range 20.98, and the time of flight remains the same. Let's erase this one and then let's do maybe 14. Now you can see the range is changing slowly because we're giving more and more power horizontally initially. However, nothing else changes, right? Initially now 14, initial height same, the range changes 24.48. However, time of flight gonna be the same because initially there's no vertical y direction, we're not doing anything. Because of that, the time is only depending on how high you actually send the object downward, okay? Let's erase this and then do maybe 16 because we closed link to the end of that path, right? So now horizontal direction, let's see whether I can measure that this way. It will be a problem, so maybe we have to bring this guy. Yeah. So you may, because it is actually all the way towards the end, this part is hiding. If I bring this, right, you can see that. So I can't read that numbers. So maybe another way to measure that is actually bring this red color circle, okay? And then get all the way to the middle of that, then you will see a number about 28. That number doesn't matter if there's a little bit of error there. This is just to check how it is changing.
Professor, I think you can zoom out a little bit on using
Oh,
the
we can. Oh, yeah,
upper left.
actually. Yeah, yes, you're correct. We can actually zoom out. Yeah, we can still measure, right? Yeah, thank you. Yep. So which means we'll measure as accurate as possible then. Okay, so we'll bring this one. Okay, so that should be now what we do in 16 and initial height 15, 27.98 and 1.75. Yep. Yeah, please do that. Okay, there's a zoom in and out button on the very top. You can zoom out. And let's increase this into maybe 18 or maybe you can go 20 because now we can actually go much further. Erase the path, fire it. Now you can see it go much further. So let's see how far it went. 34. So it's still the time is same, right? See that? So now I'm doing 20 meter per second. Initial height same. Range I can go 34.97 and the 1.75. Okay. So in the discussion section, talk about what we really observe in these two tables. There's no any other calculation or anything to do there. So you need to take a look, do a couple of sentences, what we really observing there. So projectile we observing and the projectile range is can change as a function of initial horizontal velocity increment. However, the projectile time of flight is actually depending only on vertical height, because vertical direction, we're not doing anything change. Question. Any question? Okay, so seems to be very easy, right? Then let's take a look the last table. Last table is the only one we have a little bit of calculation. Okay, so let's take a look that. We can keep the same object. Technically, object name and object mass doesn't matter. We understood now earlier, right? Doesn't matter. We can keep the same object. We don't need to worry about that golf ball and the 0.05 kilogram. And the initial velocity in this case, we can fix one number. And then what we're trying to do, we're trying to understand by changing slowly the height of the initial height of the object, where it is launching initially, and then slowly decreasing that height, we're going to measure range slowly for each case. And then by investigating time of flight and the y component and s component direction, x direction displacement, we can actually estimate, for example, time of flight we can calculate, and also x direction we can calculate how far it should go, and then we can compare those information to the measured values that actually plan for this experiment. And eventually, at the end, we can actually calculate the gravitational constant too. So that is the whole plan for this experiment. Now, how are we going to do this? Now, for example, let's go back where it was earlier. Let's erase this one. Everything else you can keep the same. I need this guy. Let's bring this back into maybe some reasonable value, 15. Let's check how far it go. Yeah, that's good. I think, oh, you can go back to 12. Yeah, that's good. Then we can keep this level of zoom, okay? Okay, now what we're going to do, initially we start at 15 meters height. Initial velocity, let's keep 12. The numbers might be different from the lab manual, doesn't matter, okay? Object name, I am using the golf ball. And then the object mass, that for our informational purposes, 0.5 kilogram. And then the initial velocity, I'm using 12.00. I add this extra 2 decimal places purposely, because otherwise after you do the calculation, it becomes very less significant figure, because if you're doing this in class situation, we can measure actually more accurate than these numbers given, okay? Just leave it like that, 12.00 meter per second. Initial height, unit meters. Now in this table, you can see I can measure range of the projectile, right? I can measure time of the projectile by using these two. Now, what's the plan here is actually calculate the time of the projectile and calculate the range of the projectile by using the standard equation which you learn in your lecture class. Okay, that's the plan. Then we're going to compare them together. Now, to do that, we have to have a good idea about how to do the calculation. Let's first finish this data part, and then I will explain you how to do that calculation. It's very simple. Okay, by now you should have a really good idea how to do it. Okay, so all we need is now launching the object with the same speed at different height, but measure the range and the time of flight. Okay, let's do that. Launch it. This we already measured earlier, but let's measure again. Now the range, 20.98, time of flight, 1.75. Now those are the information we're going to calculate in a bit here. And those are the numbers we're going to compare at the end, okay? And the next one, I need to bring this into 14 meters height now. Erase the path, click here and then drag into 14 meters. Usually I think this simulator go like 1 meters at a time. If you click and drag, it should not go anything beyond, anything in between, I think, okay? And the fire again. Now you can see it doesn't go into the same place. The whole projectile is changing now, right? So I have to click this and drag my sensor, and now new range is 20.27 and the time of flight 1.69. Erase the path, change the height into 13, refire. You can see now it's changing, right? Launching the ground location, it hit in the ground, it's actually completely different now. 1954, 1.63. Erase the path, bring this down 1 more meter, fire again. Let's measure that. It's about 18.77, 18.77, and then time of flight 1.56. Erase the path, bring this 1 meter down, 11, launch it, measure the new displacement, which is 17.97, time of flight 1.50. And likewise, let's continue. Erase the path, change the height into 10 meters, launch it, range 17.13, time of flight 1.43, okay. Time of projectile I usually call time of flight, okay. Erase the path, change this into 9, fire it again. Now the range is 16.25 and the time is 1.35. You can see now clearly, if you observe these two numbers, you can see initially this is the same object moving, and the initial condition, initial velocity we keep the same. However, height is we changing, right? As soon as you change the height, you can see time of the projectile decreasing. As a result of now horizontal displacement is also decreasing, right? So that height is actually plays a major role, because the horizontally, initially we moving the object only horizontal velocity, okay? That's why. And erase the path, change this into 8 meters, fire again, measure the displacement. Now I have 15.33, 15.33, 1.28, erase the path, change this into 7, fire again, measure the new displacement horizontally 14.34 and 1.19. Erase the path, change the height into 6, fire again. Now the horizontal displacement 13.27 and the time of projectile 1.11. Last data point we needed, erase the path. Last data point, we're going to take 5 meters height, send it, and then measure the new numbers. Horizontal range 12.12 and the time of object in the projectile motion 1.01. Okay. So we have the data set. Now all the rest is actually calculation. Okay, this should be in unit meters. And this should be in unit second, the time. And then let's check how to do this to calculation, right? Question. And as you complete, then these graphs should appear automatically. As I remember, I said it that correctly. I need to check that graph in a bit. Let's check that. At the moment, I see the graph is appear fine. We can check that in a bit, okay? Okay, so let's take a look how to do the calculation. Anybody have any question with the data? Everybody good with the data set, right? Okay, let's take a look how to do the calculation for the time. Time is depending on only y height. Because of that, I can go y-axis. And on y-axis, I can apply, for example, delta y, which is equal initial velocity v0 times t plus 1/2 times the gravity times the t to the power 2, right? That equation. If I apply that equation only y direction, initial y velocity is 0 on y direction, v0 y is 0. As a result of that, this whole component right here going to be 0. This whole component v0 t is 0. My equation will be reduced into delta y. Delta y is the y displacement I'm writing here. Okay, delta y is equal 1/2 times g times t to the power 2, right? So which means g we know 9.81. Delta y we know because we know exactly where the object is launching. By rearranging this equation, I can find the projectile time. So that's what we're going to do. So the projectile time is equal. You just need to rearrange this. Multiply y by 2 times delta y, divide by g. Okay, equation.
Can you show us the equation? Yes, please. Thank you.
Yeah, and one quick thing actually, earlier I forgot to mention you that this is a displacement, right? So the displacement has a direction, so which means all of these numbers must be negative, right? Object moving in negative direction, because you know the gravity is negative 9.81, right? We have to consider that way. There's nothing wrong really. We can do this way by putting the positive here, nothing wrong, but it's better if you put that negative sign there. Otherwise, when you do this calculation, I have to put g in positive number. Instead of that, let's apply g with the correct sign here, 9.81 meter per second is squared. And all of these numbers must be with the negative sign, okay? I'm going to change it quickly.
Shouldn't that equation be the square root because t was squared?
Correct. This should be square inside the square root, everything. Parentheses, and then you can say power half, okay? And I'm going to change all of these into negative because that's going to match with exact vector direction. It's not really anything change at all. Oh, I think I delete a few data point mistakenly. Anybody remember what's this 2 data point were? Oh yeah, this is 12 and then 11. No problem. Yeah, so that's fine. Negative, negative, negative. Let's put that sign. I forgot earlier actually, because that will give you a really better observation about this. The gravity must be negative too. Okay. Now let's calculate this one. T must be equal now is square root, right? SQRT, parentheses. I need 2 times delta y, that is this number. Don't write the number, instead of click on the cell, okay? B45. Then divide by gravity. Gravity is actually minus 9.81. Put that inside parentheses. If not, that not a problem. It's gonna still read correctly. Close bracket. Hit enter. That important, you click this cell and then put the negative sign into gravity because this is negative. As a result of that, that negative sign should cancel out. Okay, otherwise I can't take this square root. Okay, let me copy paste that function into B here. Then you can see that if needed. Okay, let's increase this a little bit. All right, so that's the function I'm using. Okay. Now this is in time second. Now you can see I'm getting exactly same number as I got earlier. Okay, see that? There's no difference at all. But since this is a calculated value by using this initial height has actually 4 significant figures, I can increase 1 significant figure if I want to here, but nothing much change. I think let's take a look if I increase 1 decimal place, whether I'm getting slightly different number. It's better, I would suggest just leave for 3 decimal places and then 4 sig fig, then you can see that actually look like slightly off. We can do a percentage error later here, okay? If I do one calculation, then to do the rest, you know what to do on the Excel now. Click on the cell, right-hand side, very bottom corner, solid green dot, click and drag. That will do rest of the calculation automatically. Let's keep 1 decimal place more, okay? Right click, format cells, numbers, leave 3 decimal places. Then I have 4 significant figures. That way I can see a little bit of error compared to previous. That's better, I think. Okay, question. Let's compare that calculation here. Percentage error for the time. Percentage error for the time. Gonna be percentage sign. There's no particular unit for that, right? So we are calculating that for the expected value, right? Expected value is actually, I can compare to any. This is measured value, that is the experimental value. Expected value here, let's say the theoretical value, that should be the calculated value, right? So let's compare these two accordingly. So which means right here, any question? Anybody have any question? Yeah, ABS, parentheses, let's say expected value is theoretically what we planning on getting, that's the calculated value, right? Let's compare to that. Minus measured value, that's the experimental value, close brackets, divide by expected value, multiply by 100. Very small percentage difference, but it's still, that's there because we increased that decimal place, right? If not, you're gonna get 0 here. You can see if I rounded these two, this one rounded, this is going to be exactly the same number. Let me copy paste that function also, maybe to here. Okay, let me increase the size of this cell. You can see that function. Now, if I do one calculation, to do the rest, you know, click on this right-hand side, very bottom solid green dot, and then drag. It will do the calculation for you. Okay, good. Any question? Okay, now let's take a look how to do the calculate, how to estimate the range by using equation, right? So in x direction, in any projectile, x direction, in x-axis direction, I have only one equation. So that is actually the range, which is actually x, is equal, range is equal, v0x, initial v velocity. I'm going to use uppercase V to clear it with the v0x, initial x-axis component of velocity, which does not affected by the gravity at all, times total time of the flight. Okay, now total time of the flight, I know the equation here. See that? So let's take a look the equation wise. I know now I can calculate this easily, right? Because I know the total time of the flight. I just need to multiply by the initial velocity, which I know 12 meters per second, then I will get the answer. But let's take a look equation point of view, variable point of view, what I'm gonna get here, right? If I plug that, let's say I have x here, which is equal v0x times, now that time component there is actually that whole part here, right? That's going to be parentheses 2 times y times 2 times y divided by g, close brackets, times half the power. That's the equation point of view, right? Okay, following? Now let's say, for example, I would like to rearrange this equation to make a graph. Let's say I have here measured values, initial height, this is actually y component, the total range, which is actually x displacement, right? This is actually y displacement. This is y displacement. And then this is x displacement. This is our data, right? So which means if I make a graph y versus x, I actually can use this equation right here to figure out, for example, initial velocity or maybe gravity, things like that, right? How to do it? You have to rearrange this equation a little bit. So first is square both sides. So then you're going to get x to the power 2. This side, which is equal v0x power 2, and then you will get other component there without any changes. Okay, 2 times y divided by g. Good, follow that? This right here, I'm writing that information. Okay, let me highlight this area a little bit. So I have y direction x equal v0 xt, and then the t is actually total time, which I already know earlier. By knowing the y-axis motion, I bring that equation and then plug it here. Then I square both sides because I have a square root here, which we don't like to have, right? If I do that, then I have an equation look like this. Okay, following? Okay, then if I keep y on one side, bring everything into the other side, this equation should be look like this. Total y, which is equal, bring all the component into the other side, g, I'm going to put it inside the parentheses, g divided by 2 times v0x squared, 2 times v0x to the power 2, close brackets, and then you have x to the power 2, okay, this side. I cross multiply by g, divide by this part right here. Then my formula look like this. Now you can take a look. If I make a graph, for example, let's say if I make a graph y versus x, I will get a formula or equation which is parabolic type. In that parabolic equation, I should be able to calculate, for example, the gravity by knowing the v0x. That's why we actually need this graph. Okay, got that idea? Question? So then one plan of the experiment, okay? So now, before we talk about the graph, let's complete this table now. Now I can do the X range, unit should be in meters, and I can do that very easily, equal sign. All I need is the V0, which is 12, right? 12 meter per second times the time, right? Total time. I'm going to use here calculated time because all of these are calculated values, right? And then I'm getting 12.98, exactly the same number. So just leave it like this, but I would think that maybe it has a more decimal places. Let's see whether it have more, yeah. But the showing more decimal places has no any meaning because of that. Let's leave it like that. But however, when you do the percentage error, usually in Excel function, it's going to read all the decimal places inside here, hidden decimal places. As a result, you will actually see some percentage error. Okay, you will see that in a bit. Let me write that function also here. What we're doing is this function, okay. That is the X range. Okay, 12 times E45. If I do one cell, then you click and drag. You can do all the other calculation very easily. Now you can see if you compare these two, this is measured on cell C, and then these are calculated on cell F. You can see those numbers are exactly match. Question. Okay, then let's do percentage error for that one. Again, there's no unit for that, but we can put the percentage sign there. Let's do that calculation. Percentage error, very similar to the previous equation right here, equal sign, ABS, parentheses. Now we comparing. Expected range is this one, that is one we theoretically calculating, minus measured is the experimental one, close brackets, divide by expected range, multiply by 100. You can see these two numbers looks the same, right? But you can see a percentage error is still the reason. Since this is a calculated value, there are other decimal places. Those are hidden now. Those are inside there actually. But the Excel function usually going to read them automatically, okay? So if you do that function for one cell, then you click and drag that solid green dot, it will do the rest automatically for you, okay? Copy paste this function also to here. Okay, so this is the function which we have. That's the function we have for the percentage error. Okay, any question? Okay, now let's take a look if you don't have any questions so far. Anybody have any question on any of this calculation? Time and the range calculation, those are the two things which we need. And then let's take a look at the graph. Okay, now this graph right here, I think the axis is flipped. So you have to actually redraw that graph. Okay, let me show you. Graph number, figure number 2. Okay, you need to remake that graph because we are actually making y versus x to the power 2. Okay, y versus x to the power 2. So please, you can get rid of that graph. Oh, actually, there's another way you can do it. If you double click here, I can change the data set. Let's do that since everything's set up here, that easier, I think. You can remake the graph. Now you guys know how to do the graphing and everything. Double click and then select data. Then you see the series right here already there. Just remove that. Then you can see all the data is disappear. Then let's add the new data set, okay? Because the axis flipped, I think. And then I'm gonna add X values as my range measured right here. Column C. And then Y values, height measured right here. Column B. Then click OK. Then click OK again. Graph looked the same, but earlier, you remember this axis shows the negative sign. That's how I figure out it's actually axis flipped, okay? So the y-axis negative sign should be here, and then x-axis should be on here, positive only. And then the graph shape should be like the downward parabola, okay? Now it looks fine. So all what I did is double click here, and then change the data. Okay, select data. Then you can delete the data set. They are already, remove it, and then re-add the data set. Then it will correct that problem. Okay. Question. Everybody have the right way of the graph now. Y-axis should be negative, goes from 0 to about -16. X-axis should be positive only, should goes from 0 to 25. I can change that limit if I want to by editing the range here, okay? X-axis, I can maybe start, we don't need to go all the way to 25. X range is going to maybe like 21. Should be good enough, be 22. Yeah. You can edit them if you click on this, any of the number right here. Then this right-hand side selection tool will appear. You can actually edit all the information on the graph, okay? If not, just leave it like that, that's okay. 25 doesn't matter. Question. Now you have to add the graph fitting again, right? Because now this is the equation we expecting. If I fit that with the parabolic curve, then I can actually extract these numbers. Okay, that's the plan. Let's fit that. You know how to add the trend line. Double click on the graph, add element, trend line, more trend line options. Then you will see this right-hand side. Couple of icons appear, new menu bar. Click on the last one on the top, trend line options. Then click the polynomial fitting, okay? Polynomial, second order fitting, then your dotted line should be perfect fit with the data. Go all the way to very bottom, click all these three, okay? All the way to very bottom, then you will see three different icons. Click all those three, okay? R square tells you how perfect is the fitting is. You can see R square is 1 because this is a simulated data. Of course, it's going to be a perfect fitting. And now what we're trying to do, we can actually estimate, for example, gravity by using this part right here. Okay, you can see number in front of the x squared should be equal to this whole part. Okay, let's do that calculation quickly here. Now I'm talking about graph of y versus x, okay? And then constant we're talking about is actually g divided by 2, parentheses 2 times v0x power 2. That whole thing is actually now equal to this number 0.0341. Now from that I can actually calculate g, right? So the g should be now equal to that number 0.0341. Then I need to multiply that, parentheses 2 times v0x power 2. v0x power 2. v0x we know, 12 meters per second. Then we can get the answer. Let's take a look at it. We can say this is gcal, and then we can do the calculation on the next cell. Equal sign 0.0341 times 2 times 12 to the power 2. If you do that calculation, we should be expecting about 9.81. So we're getting about 9.8202. So we're getting very, very perfect. Now, these are the information you have to include in your discussion, okay? In your discussion, extra information, anything you've done, any calculation about the graph, usually that calculation should go under the graph, close by the graph. Then in the discussion, you can discuss how you've done that calculation, and then what you really do in there, what kind of information we try to study there. We try to actually study the gravitational constant, and then I got 9.82, very good answer. And then let's do the percentage error also for this one. Percentage error, ABS equal ABS, parentheses, we are expecting, and this number is, sorry, I forgot to mention earlier, this number is minus, right? Keep that negative sign, then you will get that negative sign for the G. That's important, right? Because G must be negative. When the gravity is always downward direction, since it is a vector, we should actually show that gravity is actually we getting the right negative sign. Okay, that part of the experiment. Do equal ABS, parentheses, any question on this calculation part? Expected minus 9.81 minus calculated, you have that on this cell, close bracket, divide by another ABS, parentheses, minus 9.81, close brackets times 100. Let me copy paste that function also here. You can refer it if needed. Okay, that's the calculation which I done for the graph of x, y versus x. That is figure 2, okay? This is figure 2. Question. Okay, any question?
Yes, I actually have a question about the how you calculated the percent error. So I noticed that for the percent error when doing the time and the range, you used as a denominator the experimental value. But for when you calculate the percent error using for G, you use for the denominator the expected value. I
No,
wonder why the difference.
no, we always using calculated value. Expected value should be on the denominator. You can see this is E45. E45 is this time calculated value.
Okay, I understand. Thank you.
Yeah. Usually percentage error always denominator should be expected or theoretical value, or which we generally call the known number, right? Okay, any other question? Okay, let's take a look then other graphs. So the graph here is actually range versus time, right? What we can do with the range versus time. So what kind of equation match with the range versus time? Now you know all the equation which we have, right here. So if you take a look, the range versus time, always I have one formula, right? X equal V0 x times t. Let's take a look. That is range is x, which is equal V0 x times the time of flight, right? Now, if I have a graph which actually showing you that data, so this graph is now you can see look like y equal mx type graph, right? So y-axis is the range, x-axis is the time, which means if you take the slope of that graph, that should be equal to the v0x. So that's the idea. So slope of the graph, which is 11.998, and then we expecting the slope of the graph must be equal to the v0x. So we know v0x must be 12. Now we're getting 11.99, very good number. Let's compare them. So let's do the PE for this v0x expected. Let me write it down that also here. v0x expected 12.00 meter per second. From the graph, we're getting 11.998. Let's compare that. Percentage error between those two, I will compare their equal sign. ABS, parentheses, expected 12, minus, from the graph we're getting 11.998, close brackets, divide by 12, multiply by 100. Let me copy paste that function also to here, maybe, right? Okay, then let's highlight the same color. So that color represent, this whole thing actually represent graph of a figure 2, okay? I'm just gonna leave it like that. This is actually calculation for figure 2. Question. So those are the things, put all the information, the graph, data table, everything into the data section. Then if we do some calculation, it's better to show that calculation under that graph. Okay, you can copy paste this also directly since we do everything now in the Excel. Except this function, you can copy paste this part. And then the function, you can actually add into discussion section. When you do the discussion part about each table, then bring the function. By using this graph, we study this particular information, we calculate that by using this particular function, and then so on. Then you can easily write up like half a page, full page without any problem. Good, any other question? Everybody okay so far? Then let's take a look the last part right here. So we already have the graph. Now, what is this graph is, make sure the first graph I did change, okay? Remember that. I actually changed the graph axis because the Excel sheet which I gave it to you has the flipped axis. Please make sure you observe that y should be negative, x should be positive. Otherwise, that will not the way which I wrote the equation here. You will get a wrong answer. Okay, that's only the difference you have to make sure. So let's take a look then the last graph, figure number 4. So what that graph is actually, so this graph is displacement versus time, right? We know that formula, how the y displacement varies. Y displacement is equal, initial y component 0, half times gravity times t to the power 2. That's the y displacement equation, right? By using that y displacement equation, I can calculate, for example, if you take a look this graph right here, this look like a parabolic shape, right? And if you take a look the fitted equation, parabolic equation, y is equal a constant times x to the power 2, right? We can actually get rid of any other constant right here. We need only this number. So which means if I extract the number in front of t to the power 2, t is x in this case, x-axis, y is the displacement on y-axis, right? So which means if I get the number in front of here, that should be equal to this part, which is half times the g must be equal to that number, minus 4.8929. So which means if I multiply that number by 2, that should be equal to gravity. That's the idea. So the G is equal minus, G is equal, let's do the calculation on Excel, equal sign, negative 4.8929 multiplied by 2. So we're getting, sorry, I think my number 4.8929, yeah. So we're getting about like 9.7858. We're expecting 9.81. So it's a fairly reasonably close number. Good? Any question? Let's do the percentage error for that one too, because we know I can compare that, right? Equal sign ABS, what we comparing. So we expecting negative 9.81 minus, we expecting this calculated value, close brackets, divide by parentheses ABS minus ABS parentheses, okay, ABS open brackets minus 9.81 close brackets times 100. Still like that number you can see very, very small percentage error. Let me copy paste that into here. That's the function we're using, okay? So this blue color right here represent last figure. So let me write that here. This is actually for figure number 4. Figure number 4. All of those should go to your discussion section in detail. What we calculated, what's the percentage error, how we calculated, things like that. These parts which we done here, for example, this information and these calculated parts can go under the graph in your data section. Okay. Question.
How did you get the negative 9.7858 for G?
This one. So you need to multiply the number in front of x to the power 2 and then multiply by that 2. .8929 multiplied by 2. Right here.
Thank you.
Okay, any question? Anybody have any problem with these three calculation? Everybody okay with that? These three color represent three different graph, okay? Figure 2, yellow color, then figure, sorry, this should be figure 3 actually, in the green color, and then figure 4 right here in the light blue color, okay? And I think the last two graphs are fine. I did little bit of adjustment on XY axis on graph number, figure number 2, graph number 1. And then there were some calculation on table number 3. I think everybody okay with that. Table number 1 and 2, just the observation, nothing much there. I think we done everything. If you have any question, you can stay in the call. And if you don't have any question, you can log off. So I will see you guys then next week. Okay.
Professor, just one question.
Yeah.
On the calculation for figure number 2, where it says GCal, can I see that equation again?
Figure number 2 right here. This yellow color.
Right, where it says GCal. I just
This
want to see
one.
the equation
Yeah.
again.
That's the formula.
All right, so it's 12. All right, thank you.
Mhm.